any of the cloud-specific database offerings. The idea is to get a high-level overview of the different types of databases that are present and the important things that you would look for when choosing a database on the cloud. Let's get started right away. What do databases provide? Databases provide organized and persistent storage for your data. Block storage provides persistent storage, but databases help you to organize them. You can create tables, you can create relationships, you can create indexes. Databases help you to organize your data in a much better way. Now, how do you choose between different database types? Choosing between different data types is an interesting problem. And to be able to do that, you need to understand a lot of things. You need to understand what is availability, what is durability, what is RTO, what is RPO, recovery time objective, recovery point objective. Why do businesses worry about RTO and RPO a lot? What is consistency? And how does it depend on availability and durability? And what are the transactional needs from your databases? The idea behind this specific section is to help you get on a simple journey to understand all these terms and understand the variety of relational and distributed databases that are present. I'll see you in the next step. Welcome back. Let's start with a simple scenario. Imagine that a database is deployed in a data center in London. Let's consider some of the challenges associated with the database. Now, if a data center crashes or if the server storage fails, what would happen? Your database is down. The next challenge is that you will lose data if the database crashes. Challenge 1 and challenge 2 look similar, but they are a little different. Challenge 1 is related to availability. Your application can no longer talk to the database. That is challenge 1. Challenge 2 is about durability. Basically, once the database crashes, whatever data is in there is lost. So what would we do to fix this? What we can do is to add database snapshots. So what I'm doing is I would automate taking a copy of the database, and every hour I would keep a snapshot available in a corporate data center, in another corporate data center. What would happen now? Let's consider the challenges again. Challenge 1, your database will go down if the data center crashes. That challenge remains. Challenge 2 is partially solved. How is it partially solved? Because if the database crashes, you still have database snapshots. You can use the snapshots and set up the database from there. However, one thing which is important to consider is that you might lose up to an hour of data. So I'm taking a snapshot every hour. So if the failure happens, let's say 30 minutes after the snapshot is taken, then all the data for that 30 minutes is lost. And that's the reason why challenge 2 is partially solved. So we'll not lose the complete data in the database, but we will lose half an hour of data. Challenge 3 is new. When we are taking snapshots, database will be slow. So as and when I start taking snapshots out of the database, what would happen? It would be serving the application, and it will also be spending some energy on taking the snapshot. So it will be slow. So what are the alternatives? Think. Let's first focus on challenge 2. So how can we fix challenge 2 first? We can lose up to an hour worth of data. What can we do to solve that? Think, and we add in transaction logs. You say we can add transaction logs to the database. Transaction logs are nothing but what are the changes that happened to database since the time the last database snapshot has happened. What we are doing is we are enabling transaction logs on our database, and we are having a process to copy them over to the corporate data center. Now let's consider the challenges again. What's happening? Challenge 1, your database will go down if the data center crashes. Remains. Challenge 2, you will lose data if the database crashes. It is solved. Because if this database crashes, I would have almost up to the points data when I combine the snapshot with the transaction logs. You can set up the database from the latest snapshot and then apply the transaction logs. Challenge 3 still remains. Database will be slow when we take snapshots. Think, and how do we solve challenge 2 and challenge 3? That's where we add in a standby database. Now, what we'll do is we'll look at one of the options, which is to add a standby database. So what we'll do is we'll add a standby database in the second data center with a synchronous replication. What would happen? Challenge 1 is solved. What will happen if your database goes down? You have a standby database. You can immediately switch the application to use the standby database. Challenge 2 is already solved. And now it's even better. Because you have a standby database with the backup, the chances that you would lose data would even go down. Now, challenge 3 is also solved. Database will no longer be slow when you take snapshots because you can take snapshots from standby. Applications connecting to master will continue to get good performance. In this step, we focused on understanding the important challenges when it comes to databases. The solution which we have offered is not really important. The important thing is to understand the different challenges. The solution provided is neither perfect nor the only solution possible. The idea behind this step was not to focus on the solution, but to really focus on the different problems that you would face when you are talking about databases. Making sure that databases are available and the data in them is durable is a very, very challenging problem. This is even more challenging when it comes to use cases where you have a lot of data to process or when you have to do a lot of transactions, let's say millions of transactions per second. I'll see you in the next step where we'll talk a lot more about databases. Welcome back. In this quick step, let's look at availability and durability. We have already discussed availability when we talk about compute. Let's now discuss it in combination with durability. What is availability? Will I be able to access the data now and when I need it? So can I access my data when I need it? That's availability. It's measured as a percentage of time an application or a database in this specific situation provides the operations that is expected of it. Durability is a measure of will my data be available after 10 years or 100 years or 1,000 years? Is there a chance that I lose any of my data? Let's look at a couple of measures of measuring availability and durability. 4 nines is 99.99. 11 nines is 99.99999. So there are a total of 11 nines, 2 before decimal and 9 after decimal. Typically, as far as availability is concerned, 4 nines is considered to be very, very good. However, 4 nines is considered to be very bad durability. You don't want to lose data, and that's the reason why durability of 11 nines is considered very good. We already looked at this table earlier. So availability of 99.95% means 22 minutes of downtime. Availability of 99.99% downtime means 4.5 minutes of downtime, and 99.999% of downtime means 26 seconds of downtime. So you can see that achieving 99.99% availability itself is very tough. If you want to achieve 99.999%, it's almost next to impossible. Now, let's look at durability. What does the durability of 11 nines mean? When we talk about durability of 11 nines, it means that if I'm storing 1 million files for 10 million years, you would expect to lose 1 file. Most of the cloud data storage options provide very, very high durability, and achieving that durability is very tough. Now, why do we go to this extent? Why should durability be high? Because we really hate losing data. Because once you lose data, the data is gone. There is no way you can get it back. Imagine if it's a bank transaction or a financial transaction. You will not like to lose it. And that's the reason why options to increase availability and durability of databases. So how do you increase availability and durability of databases? Increasing availability is by having multiple standbys. So if one of these fails, immediately the other one picks up. Making sure that you have multiple standbys in multiple availability zones, not just in one availability zone, but spread them across and in multiple regions, so that you can protect yourself from failure of a complete region. How do you increase durability? You increase durability by having multiple copies of data. You can go for either standbys or snapshots, transaction logs, and or replicas. So you can go for any combination of these to increase the durability. And you want to ensure that this data is copied to multiple AZs, and if your regulations allow, to multiple regions. Now, until now we have been talking as if replicating data is free. The thing is, replicating data also has its own challenges. We'll talk about all these when we get to them a little later. The idea behind this step was to give a high-level picture of availability, durability, and what are the different things you can do to increase availability and durability of databases. I'll see you in the next step. Welcome back. Let's look at a couple of terminology which are frequently used from the perspective of a database. RTO and RPO. What are these and why do we need this? As we discussed earlier, you don't want to lose transactions or trades, or you don't want a stock exchange going down for an hour. Typically, businesses are okay with some downtime, but they don't want to lose data. Until now, we have been talking about availability and durability, which are technical measures. How do you measure how quickly we can recover from a failure? That's what business wants. That's where RPO and RPO come into picture. Recovery point objective is maximum acceptable period of data loss. How much time period can I lose data for? That is what is called RPO, recovery point objective. RPO is recovery time objective, maximum acceptable downtime. Within how much time should I be available again? Achieving minimum RTO and RPO is very, very expensive. And that's the reason why we have to trade off based on the criticality of data and the applications. Now, let's look at a quick question. We are running an EC2 instance, storing its data on EBS. You're taking EBS snapshots every 48 hours. So you only have one EC2 instance and you have the data of it stored on EBS. You're taking EBS snapshots every 48 hours. If the EC2 instance crashes, let's say you get a page and you think you can manually bring the instance back up in 45 minutes using the EBS snapshot. What is your RTO and what is your RPO? So your recovery time objective is 45 minutes. Your RPO right now is 48 hours because there is a chance that you took a snapshot right now and after 47 hours the EC2 instance crashes, then you are setting the EC2 instance back to the data which was in the EBS snapshot about 47 hours back. So your recovery time objective is 45 minutes and recovery point objective is 48 hours. Let's look at examples of achieving RTO and RPO. Now, let's look at a scenario. Very small data loss. So I would want to achieve RTO of 1 minute and I would want to achieve very small downtime. Let's say RTO of 5 minutes. The solutions which we are discussing in here are not the only solutions possible, but this is just to understand the alternatives which are present. So what can we do? We can have a hot standby. What we can do is to automatically synchronize data between the master and the standby. And we can have the standby ready to pick up the load when the master goes down. And you will not only have the standby ready to pick up the load, but also you will have automatic failover configured. So you will have a health check or something of that kind on the master, and as soon as the master goes down, we switch over the failover to the standby. Thereby, we can achieve very small data loss and very small downtime. In normal times, you can also take regular snapshots from standby to be even more safer. Let's look at this specific scenario. Very small data loss. I would want very small data loss, RPO of 1 minute, but I can tolerate some downtime. So I can say my recovery time objective is 15 minutes. In that kind of scenario, I can go for a warm standby. So automatically synchronize the data, but have a standby with minimum infrastructure. So if you have a standby which is ready to pick up load, then it's very expensive. But if you have a standby with just the right amount of data, but with minimum infrastructure, then whenever a failure happens, you can scale it up to handle the load. So scale it up will take a little bit of time, and anyway, we have the RTO of 15 minutes. So if we scale it up within 15 minutes, we are good. The next option is data is critical. So we have an RPO of 1 minute, but I can tolerate a downtime of few hours, RTO of a few hours. So what we can do is to create regular data snapshots and transaction logs. When a failure happens, what we can do? We can create database from snapshots and the transaction logs. The last example is data can be lost without a problem. What do you do in those kind of situations? For example, cache data. What you can do is to ignore the failed server and set up a completely new server. You want to make sure that the configuration of the old server is stored somewhere so that you can create a new server very fast. In this step, we looked at some of the examples of achieving RTO and RPO. The idea behind these lectures is to just give you an overview of different things that you need to take into consideration when you are talking about database. I'm sure you're having a lot of fun, and I'll see you in the next step. Welcome back. Now, let's take the scenario that we were working on earlier, where we had an application talking to a database. Let's extend that scenario now, and let's say I would want to add in a reporting and an analytics application. So we would want to launch a reporting and analytics application with the same database. These applications will only read data, and within a few days you see that there is a problem with the database performance. How can we fix it? Here are some of the options. One is to vertically scale the database. So I can increase the CPU and memory of this specific database. Two is to create a database cluster. If I'm using Oracle or MS SQL Server, I can create a huge cluster and improve the performance. Creating a cluster comes with its own set of challenges. Or another easy option for this specific scenario is to create a read replica. Because these applications are only going to read from the application, what we can do is to create a read replica and have the applications read from it. So we would move to this kind of a setup. We have a read replica setup for the database, and we have an asynchronous replication setup with the read replica. So that the transactional applications are not slowed down for the sake of this read replica. In addition to the read replica, you can continue having a standby where you have synchronous replication. The read replica is only to serve your reporting application, your analytic applications, and things like that. These applications are fine even if there is a small lag in the data. What would be the result of this? The result of this is that the load on the master databases would go down. Now, this also opens up a few options. If the master database goes down, you can upgrade the read replica to a master database. This kind of features are supported by some databases. Some databases also support creating read replicas in multiple regions. So you can create them in other availability zones or in other regions as well. In this step, we looked at the use case where read replicas are really useful. I'll see you in the next step. Welcome back. Earlier, when we were talking about distributing data and using a lot of standbys, creating a lot of replicas, we talked about a few problems that might result from that. And one of the problems is consistency of data. How do we ensure that data in multiple database instances, standbys, replicas, and others is updated simultaneously? This is very, very difficult challenge to meet, because if you would have a transaction going on, and if you had to wait until the transaction is replicated to all the other databases, then it would cause a slowdown for the transactional application. However, if I decide not to wait for the update to complete, what if the update is delayed? What would happen? If you read from this database, you will get one data, and if you read from this database, you will get another piece of data. That's where we have different consistency guarantees from different databases. Different databases handle this problem differently. One of the options is strong consistency. That's when you say synchronous replication to all replicas. So what you are saying is, whichever database you will read from, you will get the accurate data. You will get the point of time data. Now, this will slow down all the transactional applications as and when you keep adding multiple standbys and replicas. The other option is eventual consistency. Basically, you would say the replication is asynchronous, so there will be a little lag, a second or a few seconds before the change is available in all replicas. So if you are reading from one database and reading from the other database, for a little while, there might be a difference in data. So in the intermediate period, different replicas might return different values. Typically, this is used when scalability is more important than data integrity. Let's say you have a social media application where you have millions of transactions happening. In those kind of scenarios, scalability is much more important. You want to give a quick response back. If I'm missing a comment which was made by a friend from a few seconds back, that's okay. So examples are social media posts, Facebook status messages, Twitter tweets, LinkedIn posts, etc. A little bit of delay in these is not really a problem. The other option provided by certain databases is read after write consistency. If you are inserting new data, it is immediately available. However, if you are updating data or if you are deleting data, it is eventually consistent. What it means is if you are updating data or deleting data, there is a chance that you get the older version of data for a few seconds. A good example of read after write consistency is Amazon S3. Whenever you insert something into a bucket, it's immediately available everywhere. However, if you are making an update or if you are deleting something, there is a chance that for a couple of seconds, you might get still old versions of data. In this step, we discussed at one of the most important trade-offs when it comes to distributing our databases. Welcome back. Starting this step, let's look at the different categories of database that are present. There are a wide varieties of use cases and there are wide varieties of databases to help you meet the needs of those use cases. Let's look at a high-level overview of the different categories of databases starting this step. There are several categories of databases: relational databases, online transaction processing databases, online analytics processing databases. You have document databases, you have key value databases, graph, in-memory, and a lot of other databases. Choosing the type of a database for your use case is not really easy. What are the important factors that you would consider when you choose a database? Number one is, do you want a fixed schema? So do you want to define what columns a table should have? What relationships should it have with other tables? Or do you want flexibility in defining and changing your schemas? Do you want to go schemaless? The next factor is, what level of transaction properties do you need? Earlier we talked about consistency. What level of consistency do you need? What level of atomicity do you need? If you update multiple tables at the same time and one of the updates to the table fails, what should happen? What level of atomicity do you want? The next important question is, what kind of latency do you want? Do you want latency in seconds, milliseconds, microseconds? So what is your transactions per second? Hundreds, thousands, or millions? And how much data is stored? Megabytes, gigabytes, terabytes, petabytes, and a lot of other factors. In the next few steps, let's discuss these categories of databases and look at the use cases where they are most useful. I'll see you in the next step. Welcome back. In this step, let's talk about relational databases. Until a decade back, this was really the only option which was present. This is the most popular, or you can call it unpopular. So this is the most popular or unpopular type of database. In a relational database, you have a predefined schema. So you would say, I would have an instructor table with an ID, department name headed by first name, last name, and a phone. And I would have a course table which has a foreign key to the instructor. I would also want to have a foreign key to the department. What we are doing in here is to define a schema. This schema has tables, and the tables have relationships with each other. Relational databases can provide very strong transactional capabilities in the sense that, for example, let's say a new student is enrolling for a course. Then what I would need to do is I would need to insert a record in the student table and the course student table as well. The relational databases provide very, very strong transactional capabilities. Relational databases are typically used for online transaction processing use cases and online analytics processing use cases. Now, let's look at these in depth. Now, what are online transaction processing use cases? These are applications where large number of users make large number of small transactions. So you have a lot of small data reads, small data updates, small data deletes. So you have a lot of tables and you have a lot of transactions being made. So the use cases are most traditional applications like ERP, customer relationship management applications, e-commerce applications, and banking applications. Most of these use the traditional relational database structure for OLTP. The popular options for these databases are MySQL, Oracle, SQL Server, etc. And when it comes to AWS, the recommended AWS managed service is Amazon RDS. Amazon RDS supports a variety of relational databases. It supports Amazon Aurora, which is an Amazon customized version based on PostgreSQL and MySQL. Amazon RDS also supports PostgreSQL. It supports MySQL. It supports an enhanced MySQL version called MariaDB. And it also supports two commercial databases, Oracle database and Microsoft SQL Server. So whenever you would want online transaction processing and you want to use a relational database in AWS, you would go for RDS. The other option when it comes to relational databases is online analytics processing. Now, how is online analytics processing different? In online analytics processing, we have applications that allow users to process petabytes of data. So these are big data scenarios. For example, reporting applications, data warehouse applications, business intelligence applications, and analytics systems. A sample application is, let's say I want to decide insurance premiums looking at the data from the last 100 years. As you can see in here, we have to process petabytes of data and get some intelligence from it. This data can be consolidated from multiple databases. Most of the databases from where this data is consolidated from might be transactional databases. Now, what is the recommended AWS managed service for these kind of use cases? Amazon Redshift. Amazon Redshift is a petabyte scale distributed data warehouse based on PostgreSQL. In this step, we looked at the relational database use cases. We looked at OLAP and we looked at OLTP and we looked at the AWS services which are the right choices for that specific scenario. In the next few steps, we will continue talking about different use cases, and after that, we will dig deeper into each of these database options. We'll talk about Amazon RDS and we'll talk about Amazon Redshift. I'll see you in the next step. Welcome back. In this step, let's take a step back and compare how data is stored in relational databases for OLAP and OLTP use cases. We said relational databases are used for both these use cases and the needs for these two use cases are different. How do relational databases achieve these needs? That's what we will be looking at in this specific step. They have tables, and these tables have relationships with other tables. You have a predefined schema with a lot of tables and relationships between these tables. OLAP and OLTP use very similar data structures, but they are very different in how the data is stored. OLTP databases use row storage. So this is what online transaction databases make use of, row storage. In a single row of data, you have a variety of data. You have a username, you have his email ID, you might have his address, and other things like that. When you have transactions coming in from an online application, you typically insert rows. You will typically get data from a specific row. So the OLTP databases are optimized towards row storage. Each row of table in an OLTP database is stored together. So if I have a table with 4 rows, this is how it is stored. This row is stored together, this row is stored together, this row is stored together, and this row is stored together. So this is very, very efficient for processing small transactions. I would want to insert a record, I would want to delete a record, I would want to update a record. You can easily identify it and update it. OLAP databases on the other side use columnar storage. They store a column of data together. So if I have name, the entire values of the name column are stored together. If I have his country, all the data in the country column is stored together. So they are stored by column. Each table's column is stored together, and the benefit of using columnar storage is that you get high compression because very similar data is stored. So if I have a country column and million rows, there are probably between 200 and 300 options for countries. So you can compress this data a lot. The columnar storages can give you high compression, and also this will help you to distribute data easily. So you can distribute each of these columns to different nodes in a cluster. So I can store one column in another column in another, and another column in another. And when I would want to execute one query, I can execute it across multiple nodes. So I would be able to execute complex queries very efficiently. What do OLAP databases do? They execute a lot of complex analytics and intelligence-related queries. So it's very efficient for them to store data by columns and distribute it across multiple nodes in a cluster. The idea behind this step was to just give you a high-level overview of how OLAP and OLTP databases store their data. I'll see you in the next step. Welcome back. In this step, let's talk about document databases. What are document databases and when do you make use of them? And we'll look at what is the best option in AWS when you want to go for a document database. The document database is all about structuring data the way your application needs it. Whenever we talk about relational databases, the relational databases have predefined standards on how you have to define your tables. There are things like normal forms, tables, relationships, and all that is really, really complex. Over here with the document database, you are only focused on your application. What data does it need? And how can I make it easy for my application to get the data it needs? So instead of creating dozens of tables, you create 1 or 2 simple tables. And you don't really have a lot of structure around these tables. So these are schema-less. So it would look something of this kind. So it might just be a JSON which is stored with all the details. And one document, one JSON file might contain all the details. Another JSON might contain a few of these details. So there is a lot of flexibility in how you store data. Typical use cases are content management, catalogs, user profiles, etc. These are ever-changing pieces of information. For catalogs, for example, there might be new attributes you need to keep adding. If you go for a relational database, you need to keep changing the columns and relationships. But in a document database, you don't worry about all that. If your attributes change, then you don't worry about changing the old data. You just add the new rows with the changed attributes, and you would expect the application to take care of them. The advantages of using document database is that you can horizontally scale to terabytes of data with millisecond responses up to millions of transactions per second. Because the structure of these databases is very simple, it's just simple documents, you can easily scale them horizontally. You can store different documents in different nodes in a cluster and get very low latency, millisecond responses, and you can handle millions of transactions per second. Now, what is the recommended AWS managed service for this? It's Amazon DynamoDB. So whenever you want a document database and you are looking at AWS, Amazon DynamoDB is the most useful option. In the next step, let's talk about another form of database which is very, very similar to the document database. Welcome back. In the previous step, we talked about document database where all the data is stored as a set of documents. And in this step, let's look at key value pairs where all the data is stored as a set of key value pairs. So you have a key and the value can be anything. The value can be an object, it can be a file, whatever you would want. So key value pairs are all about using simple key value pair to store data. The key is a unique identifier. The values can be objects, compound objects, or simple data values. The advantage to this kind of structures is again that these are scalable to terabytes of data with millisecond responses up to millions of transactions per second. The thing is, I've exactly copied out the same thing from document databases to here. Because document databases and key value databases are highly scalable and they can provide millions of transactions per second. And the recommended service is Amazon DynamoDB. So for document databases and key value databases, Amazon DynamoDB is the right option. The typical use cases where key value pairs are used. I would want to store shopping cart. The key is the user ID, the value is the content of the shopping cart. You have session stores. The key is the session ID and the content of the session. You have gaming applications where you have an application state or a gaming state to be stored. So you have a specific ID to identify the user and the state of the game. And you have very high traffic web applications. So these are all the use cases where you want to go for a key value type of a database. I'll see you in the next step. Welcome back. In this step, let's look at graph databases. This would be a very, very quick step. Graph database would help you to store and navigate data with complex relationships. Typical use cases are social networking data. For example, Twitter, Facebook, or fraud detection. What do you want to do? In fraud detection, for example, you want to connect multiple transactions and identify a fraud. In Twitter, you have thousands of users who are connected to each other. In Facebook, it's the same. You have a lot of users connected to your friends, those friends connected to their set of friends, and you'd want to be able to navigate through these sets of data. So graph databases are great for social networking data and fraud detection. And the recommended AWS managed service for graph databases is Amazon Neptune. In this quick step, we were introduced to graph databases. I'll see you in the next step. Welcome back. In this last set of databases that we will be talking about, we'll be talking about in-memory databases. There are databases which are completely in memory. Why are they popular? They are popular because retrieving data from memory is much faster than retrieving data from disk. So if you are retrieving data from memory, you can achieve microsecond latency. If you are retrieving data from disk, you can only achieve millisecond latency. That's the reason why in-memory databases are useful in certain use cases. In-memory databases like Redis can deliver up to microsecond latencies while storing persistent data in memory. The recommended AWS managed service for this is Amazon Elasticache. The thing about Elasticache is actually a combination of two services, Redis and Memcached. Redis is recommended for persistent data. So this This is just a high-level classification. We will be talking about Redis and memcached in a detailed level a little later. For now, Redis is recommended for persistent data and memcached is recommended for simple caches. So if you want to create an in-memory cache, instead of talking to the database everywhere, you want to first check the cache and then you want to hit the database. So in those kind of situations also, memcached is recommended. The typical use cases are caching, if you want to do session management, if you want to create leaderboards for your gaming applications, or geospatial applications, so maps, for example. In this step, we looked at in-memory databases. I'll see you in the next step. Welcome back. In the last few steps, we talked about a number of database options. And in this step, let's quickly review them before we would get into each of these individual services in depth. When you go for relational OLTP databases, you'd go for them when you have transactional use cases which need predefined schema and very strong transactional capabilities. And the AWS service which is used is Amazon RDS. When you need relational OLAP databases, online analytic processing databases, for example, for your reporting, analytics, business intelligence applications, these databases use columnar storage, so they store a column of data together. This helps them in distributing the data from a single table among multiple nodes in a cluster, and also it enables them to achieve high compression. And the recommended AWS service for these kind of applications is Amazon Redshift. The next set of databases are document and key databases. These are very, very useful when your applications need quickly evolving semi-structured data. So we are talking about schema-less databases. Different rows in the same table might have different elements present. These databases can scale to terabytes of data with millisecond responses, and they can handle up to millions of transactions per second. The typical use cases would be when you have a content management application, or you have an online application where you show a user profile or shopping cart, session store, and also gaming application. These are all the places where you need millisecond responses and high scale of transactions and high scale of data. The next category of databases is graph databases. These are used when you have data with a lot of complex relationships. For example, social networking, or if you want to do fraud detection, you want to see the network of transactions which has happened. And in those kind of scenarios, you would go for the AWS service, Amazon Neptune. Now, when you go for in-memory databases or in-memory caches, you go for in-memory databases and caches when you need microsecond responses. The service in AWS which provides that is Amazon Elastic Cache. You can use Amazon Elastic Cache as a cache in front of the database. You can set up Amazon Elastic Cache as a cache for the data you store in RDS. If you have very, very simple caching requirement, then memcached is recommended. However, if you want an in-memory database, that is in-memory persistent data, then the recommended solution is Elastic Cache with Redis. I'm sure you are excited to look into these databases in depth. I'll see you in the next step. Welcome back. In this step, let's quickly look at a few questions based on whatever we have learned in the last few steps. Let's get started with a simple scenario. You have a startup and you have quickly evolving table structure. RDS. What would you go for? So when you have quickly evolving table structure, you don't want to go for schema-less as much as possible. You need to keep things simple at the start, and once you know what you want, maybe you can switch to a proper schema with high transactional capabilities. So start up with DynamoDB, and maybe over a period of time, you can go for a more relational database. The second question is transactional application, which needs to process million transactions per second. In this kind of situation, there is only one option, which is DynamoDB. While relational databases are awesome in ensuring that your data is really, really consistent and you have strong transactional capabilities, they cannot scale as much as DynamoDB can. Next situation is very high consistency of data is needed while processing thousands of transactions per second. And the obvious choice here is to go for a relational database. So it's Amazon RDS. Next question is caching data from database for a web application. For example, let's say you want to cache data that is coming out of RDS and that's being used by a web application. We would go for a cache. So it's Elastic Cache. And the recommended option, because you're just going to use a cache, and if it's a very simple cache, then you can go for Elastic Cache with Memcached. The last scenario is a relational database for analytics processing of petabytes of data. So we are talking about huge amounts of data, and we are talking about relational database. So we are talking about Redshift. So this is very, very good for all your data warehousing big data scenarios. In this quick step, we will take a few questions to help us review all the things that we have learned in the previous section. I'll see you on the next step.